The first mechanism we're going to look at is something called SN2. And SN2 stands for substitution nucleophilic bimolecular. And what the bimolecular means is two things are reacting in the rate limiting step. So if you go back to kinetics, you'll remember that a bimolecular reaction in the rate limiting step means in that rate limiting step you have two things colliding and controlling the rate of the reaction. Okay, in an SN2 reaction, you have what's called a concerted reaction, that as the nucleophile comes in, the leaving group leaves. So it all happens in one step. And if you look at this, this little mechanism here, what you'll see is the nucleophile is coming in with its electrons. And as the nucleophile is coming in with its electrons, we're showing the leaving group leaving at the same time. Remember, I've been emphasizing to you that if something is stepwise, we show it in individual steps in our mechanism. But if it occurs in a concerted way, we show it as occurring all in one step. Here, because this is a concerted mechanism, what you have is a nucleophile coming in as the leaving group is leaving, so we show both arrows at the same time. This is substitution nucleophilic bimolecular. You have both the nucleophile and the substrate as the two components of the rate limiting step. And so here's the question: how many species are in the rate limiting step? 2. The transition state, that's when bonds have been broken and no new bonds have yet been formed, or you can say the bonds are being broken as the new bonds are forming. It is a complex where you have a partial bond here and a partial bond here. Notice that we have these lines over here and a negative. This entire thing has a negative charge. Where is the negative being held? Some of it on the nucleophile and some on the leaving group, leaving a del positive on the carbon. Okay? So both the nucleophile and the leaving group, you could say, have a half negative charge, or maybe even more than half a negative charge, and there's a large del positive on the carbon. So this is the transition state. Once the transition state is left, the leaving group has come off, and the nucleophile is now attached where the carbon is. Notice there has been inversion on this carbon. It was that the leaving group was on this side, and these three groups were angled backwards from the way they are now. So what we see is an umbrella-like inversion on the carbon center. So this is what the leaving group looked like, and this is what the substrate with the leaving group on it looked like, and this is what the substrate with the nucleophile on it looks like. Notice the leaving group is on this side with all these groups. Now what happens as the leaving group leaves, these flip over to this side like this, and the nucleophile is attached. On the Moodle website, I will post a link to an excellent web page that goes through this in a movie, and it's very understandable. Several people have commented they watch it over and over and over again, and once they've watched it a few times, they understand SN1 and SN2 completely. SN2 reactions are called backside attacks. The nucleophile is coming in on the side opposite the leaving group, and so you can consider this the backside of the carbon, and so the nucleophile is coming in on this side as the leaving group leaves. The carbon does become inverted. If this is a chiral carbon, this will be chiral afterwards. You can figure out whether it's R or S beforehand, and then depending on the priority of the groups, it will become inverted It can change depending on the nucleophile and its priority, but oftentimes you'll see R becomes S. It all depends on what the priorities of the groups are, though. Here's an example. This compound is actually S2-iodo-propyl cyclopentane. So this is the S enantiomer. Here comes this nucleophile. What's a nucleophile? A negative charge on this sulfur. So the sulfur is a nucleophilic atom. It comes in. When it does come in, it's going to come in from behind the page. Okay, as it comes in from behind the page, the iodine is going to leave out the front. Notice, look what happens to the hydrogen. It was back. These two groups stay in the same place. The hydrogen was back, but once that sulfur group comes in, the hydrogen flips forward, and that's showing the inversion taking place. Okay, go ahead and try to figure out what is the product of potassium cyanide with 1R, 3S, 1-bromo, 3-methyl cyclohexane. The first thing you have to do is draw the carbon product. Cyclohexane on the number 3 is a methyl, and on the number 1 is a bromo. And then make sure you have 1R and 3S. And then react it with potassium cyanide. This is the substrate, the carbon substrate. Potassium cyanide is the nucleophile. What part of it is nucleophilic? Not the potassium that has a positive charge. It's going to be the cyanide, and the negative charge is on the carbon. So that is a nucleophile, and it's going to come in from behind on this carbon. It has to be backside attack. So then the bromide leaves, and what you have is the cyanide is then attached trans to the methyl group. The product is 1S3S. The reaction profile for an SN2 reflects the mechanism. Notice, because it is SN2 is a nucleophile comes in as the leaving group leaves, this is all one step. There's not where there's an intermediate. So what do we see in the reaction profile? It's just one hump. Okay? The transition state right up here is where you have the nucleophile coming in and the leaving group leaving. There's a large positive on the carbon right here. It's not being shown, but there is a positive charge on the carbon when there's nucleophile negative coming in and leaving group leaving. And what do we end up getting? We get inversion, and here we're showing it as an exothermic reaction. This is the reaction equation reflects that one step also, because it is the substrate and the nucleophile reacting together. Remember, SN2 is bimolecular in the rate limiting step. The rate is going to have both of those two components in the rate equation. So the rate equation is rate is equal to K times the concentration of the substrate times the concentration of the nucleophile. It's only one step in that reaction, and that one step is the rate limiting step. And so what happens when you increase the concentration of the substrate? Well, you're going to increase the rate. If you double the concentration of the nucleophile, you double the rate of the reaction. So the concentration and the characteristics of the substrate and nucleophile are very important. And anything that affects the energy of the transition state will be important.